If it's exam time, then it must be photocopying time for most students, right? But as you intelligently source study materials from all over and photocopy them for your own ready reference, have you ever thought about this wonderful machine that gives us the exact replicas of your source books? If you think it's only about imaging, think again. Because this is physics in action, out of the books and straight into your study space. How? What is the principle behind this amazing device? We'll find that out in this episode. Welcome to the episode on Coulomb's law. Popular knowledge about charges is that opposite charges attract and like charges repel. I'm not sure though how many of those who say it know the physics behind it. You and I will discover that part in today's episode. In this episode, we'll learn about Coulomb's law to calculate the force between any 2 point charges, superposition principle for electrostatic force on a charge due to multiple charges, and we'll crack the exam code in the exam decoded section. Coulomb was a French physicist. His experiments on the distribution of charge over surfaces and the study of the behavior of static charges led to the development of Coulomb's law. Coulomb's law states that the magnitude of the electric force between any 2 point charges Q1 and Q2 is directly proportional to the product of the charges and inversely proportional to the square of the distance r between them. That is, the magnitude of the force F is equal to K Q1 Q2 over r squared. Here K is a constant and is equal to 1 over 4 pi times epsilon naught, where epsilon naught is called the permittivity constant for free space. In SI unit, epsilon naught is approximately 8.85 times 10 power minus 12 Coulomb square per Newton meter square. Using this, K is equal to 1 over 4 pi epsilon 0 is approximately 9 times 10 power 9 Newton meter square per Coulomb square. But every force needs to have a direction. So how do we figure out the direction of Coulomb's force? Coulomb's force between any 2 charges is directed along the line joining the 2 charges. Coulomb's force F is attractive if the 2 point charges have opposite sign, and it's repulsive if the 2 charges have the same sign. Let's now tackle a quick question. For a given pair of charges Q1 and Q2, where Q2 is 2 times Q1, which one of the following statements is correct? A. The Coulomb force that Q2 exerts on Q1 is more than the force that Q1 exerts on Q2. B. The Coulomb force that Q1 exerts on Q2 is more than the force that Q2 exerts on Q1. And C. Both Q1 and Q2 exert the same magnitude Coulomb force on each other. Don't let me catch you thinking that Q2 exerts a larger force on Q1, because that's not correct. And here's why. The correct answer is C. That is, both Q1 and Q2 exert equal magnitude force on each other. We could have guessed this from Newton's third law, which says that whenever an object exerts a force on another object, the other object must exert a force which is equal in magnitude and opposite in direction. We can see from the expression for Coulomb's force F is equal to K Q1 Q2 over r square that the force on each charge is the same and depends upon the product of the 2 charges. And now we have with us a student who wants to ask a question. Let's see.
Hello ma'am, I'm Neha Joshi. I have a query. The form of Coulomb's law looks very similar to the Newton's law of universal gravitation. Can we compare and contrast them?
Excellent question. The form of Coulomb's law looks very similar to Newton's law of universal gravitation. Can we compare and contrast them? Well, both laws look similar. yet are so different. Newton's law of universal gravitation is the gravitational force Fg is equal to G m1 m2 divided by r square. Let's explore more. Both the gravitational law as well as Coulomb's law follow inverse square law, so that if the distance between the two objects doubles, the force between them gets reduced to 1/4 of the initial value. Gravitational force is always attractive, but an electrostatic force may be either attractive or repulsive. This is because there's only one kind of mass. We do not have a concept of negative mass. However, electric charge can be of two types, positive and negative. The direction of electrostatic force that two charges exert on each other is along the line joining the two charges, just like the direction of gravitational force between two masses. Since the Coulomb's force is a vector, the law can be written vectorially. F12 can be written as K Q1 Q2 over r square times r12 cap. Here, F12 is the force on Q1 due to Q2, directed along the unit vector r12 cap. Similarly, the force on Q2 due to Q1 will be directed along r21 cap as shown. I'm sure it is clear to you now. Keep questioning and keep excelling. To facilitate this is our website topperlearning.com, just a click away. The best way to understand physics is through real life. Well, let me put it this way, that physics is about real life. And so is Coulomb's law. You can find it all around you, even in your birthday parties. Surprised? I'm talking about balloons in birthday parties. Did you know that these fancy balloons also tell you something about Coulomb's law? When you try to stick a balloon to the wall, nothing happens. But if you rub it with cloth and then try to stick it, it sticks. How is this happening? By rubbing cloth against a rubber balloon, what did we actually do? We gave the cloth and the balloon equal but opposite type of static charge. This charge on the balloon caused it to stick to the wall. The force that causes this attraction is called electrostatic force. You must have felt it when brushing dry hair with a plastic comb on a dry summer morning, or when walking on a plastic carpet wearing woolly socks. To measure this peculiar electrostatic force, we employ Coulomb's inverse square law for force between two-point charges and superposition principle. The theory is done, and it's time now to throw a question at you. Can you tell how much a microcoulomb and nanocoulomb are? Think about the question. I'll answer this on the other side of the break. Stay tuned.